So you just got these blocks, but they're actually magic blocks, okay? So you have to work with me here. So I'm putting some water on here. It only works with water. And so if I slide it this way, see the block doesn't slide? And I can let you guys, if you guys want, no one ever wants to do this, but if you want to try it on your own, you can. I'm not doing anything tricky with my hands at all. But if you slide it this way, it's going to go right off the table. Yeah. Yeah, exactly. What? It's just a block, right? How in the world? It has to do with lift. So this is basically a bearing. And so we use this in industry a lot. So this is, I don't know if you can see it down here.
Oh, yeah, it's shorter.
So there's I mean, it's not much. You can't see it from where you are. The light you can see it better, but basically they just took one pass of a mill. I'm not sure what depth it was. Probably not optimal. But basically, there's that piece right there is a little deeper, not by much, hundredths of an inch. And so there's like a little cavity here. So if I slide it this way, what do you think happens? Here's the block. Here's this cavity, right? I slide it this way. Here's the table, some water here. What's going to happen in the water here, do you think? Especially like right when you go from here to here. You only have so much water here. It's going to try to conserve that volume, right? So what's going to happen to the pressure of the water if you're sliding that way? Any idea? It's going to decrease, right? It's going to want to decrease. It might not be able to because water can't, take tension really. It might cavitate or something, but it's going to try to decrease. That's going to basically, suck the block down onto the table. And that's why when I slide it one way, this way, or maybe I should do that way. It doesn't go anywhere, okay? Now, let's say I change the direction. So it's sliding this way. And I could do this different ways. I could say this is stationary and this is sliding, but what I'm actually doing with the table is like this. So if that's sliding that way, what's going to happen? And actually the water should be higher. I should have drawn it so the water's above the groove. So the water comes in here, then suddenly the amount, the volume here decreases, right? So it gets compressed. So what's going to do that to the pressure of the water? It's going to increase the pressure. So it turns out, and we're going to solve this problem next week with the Reynolds equation, but you get some kind of pressure profile like that. And this is basically lift. And if you have enough lift, it maintains the film here so that the block's not touching the surface. So that's called hydrodynamic lubrication. So that's basically one mechanism we can use for lubrication. So we'll get confused because it's hydro because, think water. But it could be any fluid. It could be air even. It could be gas too. So this one's a little different because the whole part here is cut off. And the only ways you can see it is there's a little line right here. So this part is deeper than this part. So this part is that part, right? So maybe I can mark it for you. So if I slide it that way, right? It should create lift, right? So I'm going to turn it around so I don't slide off the table. And it does. So you see how it slides along? It's not quite as good, but it works. If I go this way, well, it still slides. This one's a little bit, might be the edges too, but it works for the most part, okay? This one's about the same thing. All this is machined off. This is deeper here than this, okay? And so basically everything we did, if I slide it this way, it should lift off, right? So I'm going to slide it this way. Uh-oh, it's not working at all. I'm going to slide this way. A little water. Okay. Yeah, see, it works a little better that way. This way it gets stuck. You can see it worked a little better that way, right? This way it gets stuck. So that's opposite what we did, because there's my arrow. See? So based on this, this way should lift off. And this way should get stuck to the table, but it's not. And there's other things on here. There's meniscus, so if you don't get it just right, and the roughness does play a role in the edges here, so it's not perfect, but for the most part, if I am patient with this and slide it just right, get a lot of water in there, it slides. If I do this way, it gets stuck. I can't make that slide that way. But why is it not working now? Just like this, except, when it's cut all the way across, there's no piece of material here. And where's that pen? So the center of gravity is somewhere over here. And so what happens is, if you cut, that actually is the optimal geometry for a step groove, or step, we call this a step bearing. And we'll go through that next week. That length, if it stayed parallel, is the optimal length. The problem is this causes it to tilt down, so when you put it on the table, it actually goes like this. Right? It falls down. So then, when you slide it this way, this gap here opens up, causes negative pressure, but if you slide it the opposite way, maybe I should erase some of the other lines so you can see what I'm talking about here. Looks kind of like that. And these distances are really small, so it goes kind of like that. So then you have, what we call this here is a converging gap. That's what people who work on hydrodynamic bearings call this, because you have to have this converging gap where the two surfaces are coming together for it to work. The bearing has to have that for it to work. Okay? And so when you have that, it's pressurizing the fluid again, and these pressures will look, kind of like this, more curved. And we'll solve one of these, each one of these. Because basically this is one of these on its own is what's called an incline bearing, where you have an incline. And it's kind of like hydroplaning, And this can happen with tires, similar things, with shoes, if you go skimboarding, it's kind of a similar effect, on the beach. Similar thing to that, okay?